Hello! This video is for Module 2, Part 2, and includes a discussion of automating model fitting and k-fold cross-validation. Okay, let's go ahead and get started then. So the data set that we're going to use for Module 2, Part 2 is the data from the World Health Organization. And what we have here is various countries around the world, and the main outcome is going to be life expectancy. There are several fields in this data set, as we can see here. Some of them are just informational, like what country and what year the data was collected on. There is a variable for whether or not the country is developing or developed. And then there are several predictor variables here. Adult mortality rate, infant death rate, all the way down through here, years schooling. I think there's a total of 13 different possible predictor variables in this model. Again, the response that I care about here is life expectancy, and that is over here on the right, and that is listed for each country and then also for each year here. When we fit the model, we're going to use data from just the most recent year. Okay, so we're going to use data just from 2015. We will ignore data for years other than 2015. Okay, so the goal is to obtain the best possible predictive model for life expectancy. And we're going to use k-fold cross-validation to measure the true predictive ability of the model. So with this data set, there are, as I mentioned, 13 different possible predictor variables. There's going to be many more than that if we were to consider interaction terms or other types of terms with these variables. So this data has potentially many different predictor variables that could be used. There are analytical methods that exist to identify which predictors should be used in a predictive model. One such method is the LEAPS package in R. The LEAPS package considers all possible subsets of the predictor variables. Okay, so the way that LEAPS operates is that suppose I just want one predictor variable in the model, LEAPS will go out and find the best predictor variable for that model. Or if I'm looking for two predictor variables in the model, it will identify what is the best combination of the two predictor variables to be using for that model. Another element of finding an optimal model is to decide what metric you are going to use in selecting that best predictive model. In this course, we've primarily worked with R² as our metric of choice, and we're going to continue to do so in this class. However, data scientists and statisticians alike understand that there are other metrics that can be used. Metrics such as adjusted R², Mallows CP, Bayesian information criteria, or Aiken information criteria. Of these that I've listed here, Bayesian information criteria is probably the most popular. Okay, so let's consider the following plot that was obtained from the LEAPS package. On the x-axis on this plot, I have the number of predictor variables. Now typically we want that to be low. If I can build a quality predictive model, a model that will do good in terms of predictions, with a low number of predictors, that's good. The y-axis here is the R² values from those models. We want the R² to be as high as possible. So when I'm looking at this plot, what I would like is to be in the upper left-hand corner of this plot, because that is where the number of predictors is small and the R² is high. So for example, I wouldn't want a model with just one predictor because the R² here is below 82%. When I go to two predictors in the model, my R² jumps up to about 87%. Good candidates for the number of predictor variables here look like 4, that's that dot right here, or maybe 6. When I increase to 6, I do gain a little bit in terms of my R². Not a whole lot, as we'll see down below, but I gain a little bit there. I'm going to guess that 4 is probably our best model. So the COLAB document can be used to identify what are the predictor variables. So what predictor variables should I use when I have 4 predictor variables in my model? They are adult mortality rate, hepatitis B, so that's an immunization rate for children. I have an HIV/AIDS rate of death. And then I have a human development index, and that index is based on income. That is an important indicator to help us predict life expectancy. Now this model here has 4 predictor variables. It's this model that obtained this R-squared here, so about 88 or 89% it looks like. When I move to a model with 6 predictor variables, I am going to add in an infant death rate and also an under 5 death rate. So these are just variables that are related to the death rate of children. Again, I'm going to gain a little bit with those 2 additional predictor variables. Here is the linear model regression output for the model with the best 4 predictors on the left and the model with the best 6 predictors on the right. You can see that the model with the best 4 predictors has an R-squared of about 88.8%, so just shy of 89%. The RMSE is at 2.61. When I go to 6 predictor variables, I move my R-squared up slightly to just over 89%, and my RMSE comes down a little bit. So now you can decide if you think that a model with 6 predictor variables is better than a model with 4 predictor variables. There is certainly some gain here. Okay, so there's some subjectivity here in determining what model you think is most appropriate or optimal. I'm going to go with the model with 4 predictor variables here. So gaining just a little bit in the percentage R-squared, and I'm just losing a little bit in my RMSE here. So I'm going to go ahead and decide to use the model with the 4 predictor variables as my final model here. Okay, now let's talk about k-fold cross-validation, at least automating k-fold cross-validation. In Module 2.1, the cross-validation process was done manually. That is, the observations were manually assigned to a fold, where each fold had approximately the same number of observations. And then I wrote a custom function that went and created the models for each of those and obtained the predictions. Here we're going to use a caret package in R, and that's going to automate all of this cross-validation stuff. So we're going to use the caret package here. We're going to use a caret package when I do split sample cross-validation in the next module, or when I do Monte Carlo cross-validation. We're going to want to use the caret package to do this. It's going to make our programming life a lot easier. There does exist an analogous package called scikit-learn for Python. So Python, like R, has the ability to automate this process of doing cross-validation. How do I do cross-validation with the caret package then? It basically has 2 important components. The first is the train control, which is going to specify the type of cross-validation method you're going to use, and then also the number, which is going to specify how many folds you're going to use in your cross-validation. The number could also be used for the number of repeats that I'm going to do when I do split sample or Monte Carlo cross-validation. The train component of caret simply specifies the form of your model, what data you're going to use. Here is your cross-validation specifications, which are again specified in train control here. The method specifies what type of predictive model you're going to use. We're going to use a linear model here, but later on in the course we're going to use random forest or RF, or we might do some k nearest neighbors, which is specified with KNN. The metric is to be used for selecting an optimal model. We're going to use RMSE here for a linear model. And then the NA action just simply specifies what to do with missingness in your data. So here is the code. You can see that I have specifications here under train control, and I have some specifications under train. Again, these have to do with your cross-validation, and this has to do with the actual fitting and predictions. Here's what the output looks like when I apply this code here, which is k-fold cross-validation. I'm using 8 folds. So my k here is 8 in this example. The output is fairly straightforward here. It just tells you what type of predictor model is being used. It is telling you what type of cross-validation is being used here. So this is k-fold cross-validation with 8 folds. And then most importantly, I have my outcomes from the cross-validation. So this is going to be my RMSE. Okay, now this has been averaged over all the folds. So there was a total of 8 different RMSE values that were obtained, and this 2.73 is the average of those 8. The overall value for R squared is 87.7%, and my mean absolute prediction error, which R denotes that just MAE for mean absolute error, so they dropped the P in that labeling, but MAE is just the mean absolute prediction error. And that's at about 2.08 over these 8 folds. You can obtain the values from each fold. So here's the RMSE, R squared, and MAPE from fold 1, fold 2, all the way down through. Again, I've specified an 8-fold cross-validation, so I have outcomes from 8 different resamples or samples. The average of this column here is the 2.73. That is what is reported here in this output. The average R squared is 87.7%. So if you take this middle column and average all those, you're going to end up with 87.7%. And likewise here for the mean absolute prediction error. There are other summaries that you could obtain. Things like where is the smallest R squared or where is the largest R squared. Okay, so this output here just shows you the minimum and maximum and then the count of how many are included there. So let's see here. The maximum R squared is occurring at 94.7. So that's going to be in fold 3. It looks like that was the fold that had the best predictions, or at least most accurate predictions. Where is the smallest here? Looks like fold 1 is the smallest at just about 80%. Okay, so again, what's happening here when we make predictions for fold 1 is excluded. We build a model using folds 2 through 8. We take that model and we predict back for the observations in fold 1. And then this RMSE, R squared, and mean absolute prediction error are obtained from those predictions. Okay, and then we repeat that right for each fold. Another thing that you could do is just plot out these values. So if I take these values here, these 8 RMSE values and 8 R squared values, and just plot them out on a chart or a plot, you can kind of see what's going on with those different values. So over here on the right is the R squared. You can see that the lowest, it's kind of small, it's kind of hard to see that. Maybe zoom in a couple notches here. The smallest is at about 80%. I think that was from fold 1, was it? And then the highest was almost at 95%, which was from fold 3, I think it was. So this kind of gives you an idea of what's happening to the R squared over the different folds. The same thing for the mean absolute prediction error and the RMSE here. Okay, so when we are trying to determine or communicate what is the true predictive ability of this model, we're going to want to report this mean absolute error or this RMSE or this R squared quantity. So these quantities here, or these produced here by the caret package, should be used to communicate your true predictive ability of our model. All right. Now, there is not necessarily the same level of clarity in how we should obtain the predicted values. What I mean here is the final set of predicted values. Okay, we have 2 options to get our predicted values. So now I'm talking about after we've obtained a final model and after we've pushed that final model through the cross-validation process. There's 2 different ways that we can get the predicted values. The first is to just go ahead and use the final model. So this final model that we had up above here, before we went into the cross-validation process, this here is my final model. I could just use this model, which was based on all of the data. So this model here, okay, before I went into the cross-validation, this model was obtained using all of the data. So this model output here was obtained using all of the data. I could get the predictions from that model. Now that has the advantage that it's using all of the data in the data set to obtain those predictions. The disadvantage, right, of using all of the observations, that I don't have a true ability to understand, or excuse me, I don't have an ability to understand the true predictive ability of the model. Method 2, I could use the outcomes from the k-fold cross-validation procedure as my final predicted values. Okay, so what do I mean by that? Remember, when I was looking at the observations in fold 1, what we did is we took the data from fold 2 through 8, built a model, and then we predicted back for fold 1. So I would have predicted values here for fold 1. Now that is based on a model from folds 2 through 8. I mean, that's how I got these RMSE values and this mean absolute prediction errors, right? Was to get the predicted values for fold 1 and then compare them against the actual. So I would have predicted values for each of the observations when I do cross-validation. I could use those as well as my final predictions. So we have kind of two options here when we're talking about our predictions. Now in practice, oftentimes the predictions that I get from method 1 and the predictions I get from method 2 are going to be really similar. So for Afghanistan here, I have 62.16. That's from the final model. Or if I'm using the predicted values from my cross-validation process, I have 61.76. So off a little bit, but pretty close there. Albania, 76.35, 76.52. Again, these are pretty close. And that's generally going to be the case. Now, what is better than k-fold cross-validation? Well, we could do repeated k-fold cross-validation. Repeated k-fold cross-validation is simply a variant of k-fold cross-validation in which the k-fold process is repeatedly applied to the data. Okay, so when I use k-fold cross-validation, I am getting a predicted value once for each observation. Well, if I use k-fold cross-validation, I could get a predicted value several times. Now, for demonstration purposes here, I'm just going to do k-fold cross-validation 5 times. Usually when we do this in the real world, we're going to maybe have that be 50 times or 100 or 500 or some large number. So the only thing that I really need to change when I want to do repeated k-fold cross-validation is to just add repeats as one of my arguments in train control. So here you can see that I have repeats equal 5. That just means I want to do 8-fold cross-validation a total of 5 times. My method has to change from CV to repeated CV here as well. The output looks very similar. Under the type of cross-validation used, you can see that I'm using 8-fold, but it has been repeated 5 times. I'm again getting these measures here of RMSE, R-squared, and mean absolute prediction error. But these now are going to be based on 40 different outcomes, not just 8 different outcomes. So you can see from my summaries here that there's a total of 40 different mean absolute prediction errors that are going into this average. There's a total of 40 RMSE values going into this average. There's a total of 40 R-squareds going into this average. Again, 8 folds, but that was repeated 5 times. Here's my graphs based on 40. You can get a little bit of better idea of what's going on with the different mean absolute prediction errors, root mean square errors, and the R-squareds. Again, they're staying here. Lower end's 80% and higher end could actually reach up above 95% here. Generally speaking, this is a good model. Okay, we're doing a pretty good job of predicting life expectancy based on the 4 predictor variables that we're using here. Now, when I'm getting the predictions for a repeated k-fold cross-validation, here again I have 8 folds with 5 iterations. So let's just look at the predicted life expectancy for the first observation, which is Afghanistan. So for Afghanistan, on the first iteration, Afghanistan was actually placed into fold 6. Its predicted life expectancy from that iteration was 62.20. And then we repeated that, right? So the second time through, Afghanistan was put into fold 8. Fold 8, okay, the predicted life expectancy when it was in fold 8 was 61.79. And then this is repeated 5 times because I wanted 5 iterations. And then what the logical thing is going to be to average these predicted life expectancies across these 5 iterations. This notion is called an ensemble, okay, where I'm taking several predicted values and I'm averaging them. When I do that, I get an average of 61.94. So this is a pretty good guess. Okay, it's going to be actually better than if I were to do k-fold just one time. Okay, this is going to be an average predicted life expectancy for Afghanistan over 5 different repeated cross-validation processes. And then I'm going to do the same thing with the second country, right? Albania. Albania was in fold 2 the first time through, was in fold 4, then 7, then 2, then 6. Again, you can see that I'm getting slightly different predicted values because I'm using actually 5 different models here to try to get this life expectancy. And then I'm going to average those and ensemble those together so I get 76.30. So when you're getting the output in your computing software here, you can see Afghanistan had an average of 61.94, or excuse me, had a predicted life expectancy of 61.94 when cross-validation was used. That's that same 61.94 that I computed here for you. Albania had a predicted life expectancy of 76.30. Again, that's that 76.30 here. And then we're going to do that, right? I'm just showing you the first 2 countries here, but this is done for all 170 or 180 countries that we have data for. And that's just these values here. Again, you're going to notice that these are pretty similar. They're not too far off. These here were from the final model. Again, the final model is just the same, getting the predicted values from using all of the data. Now this is, just pay attention here, this is the predicted life expectancy for the final model is 62.16. Again, that's using all of the data, right? That's going to be the same up here, 62.16, when I was doing just single cross-validation. Because the predicted life expectancy under the final model isn't really using the cross-validation, right? It's just using all of the data and the model that we fit up above there to get those predicted values. So these here do not depend on what cross-validation process you're using. The ones on the right do, because they're actually based, these predictions are actually based on the cross-validation. Okay, a little bit of investigation using these predictions, and actually for this information down here, I went ahead and just used the predicted life expectancy on the final model. As I said earlier, it doesn't really matter because they're not that different. Okay. So here I'm doing just a little bit of an investigation between developed and developing countries. There's a wiki entry here for how countries are labeled as developed or developing. Now, this data was actually from the World Health Organization. I don't know how they did their designation, but this will just give you some information about how that could be done. When I look at the developed countries, there's a total of 22 that are labeled as developed in this country. Okay, and again, this is data from 2015, is it? That was the most recent year I had. The average predicted life expectancy for the developed countries is just short of 80 at 79.8. But if I go to developing, that drops to 69.9, so just short of 70. There's about a 10-year difference here in the average life expectancy between developed and developing countries. So it's quite advantageous to live in a developed country. We also have the minimum. So of these 22, the worst country was at about 73.5 years old, and the best was at 82.4. Of these 143 countries down here, the worst was 51.7. part of the task is to have you identify this country here, and then this country here as well. You can see, though, that there are some countries in the developing bucket, right, that have pretty good predicted life expectancy here. 81, that's pretty high for a developing country. You can see that in the actual versus predicted life expectancy plot as well. The salmon colors are the developed, and the kind of the teal colors are the developing countries. Up here, we have a lot of the developed countries, okay, but there are some teal points in here, some developing. Again, part of the task is going to have you to try to investigate some of those countries. And then here, you can also, back in here, you can see some of the developed countries are lagging behind some of the others here. They're in amongst the teal points here. There's kind of some unique unique outcomes here that we want to maybe investigate a little bit further. Okay, I am going to provide a second video for you for completing the task. It has you going in and changing some values in the code. So I want to go ahead and create a second video then that will show you how to complete the task here. So that'll be posted right underneath the video here that was for the notes. Okay, that's all I have for Module 2 Part 2. Thanks for listening. Bye-bye.